Hey, Happy New Year's, and today we're going to discuss the law of conservation of energy, section 9.7 in your book. What you should get from this section is that you should be able to state the law of conservation of energy, and you should also be able to apply it to some real-world examples. In other words, discuss some real-world examples that use the law of conservation of energy. This law says energy cannot be created and energy cannot be destroyed. It only can change form. Example, when you climb the stairs in the Who's the Most Powerful Student activity, you did some work as you climbed those stairs. You were raising your body weight a certain height. Okay, when you got to the top of the stairs, that work was changed into potential energy. Now, and I don't recommend that you do this, if you jumped off the back of those stairs, your potential energy would go down because the height would go down, and your speed would go up. So you would be creating something called kinetic energy. Not creating really, but transforming that potential energy to kinetic energy. And the farther you fell, the less your potential energy would be, but the greater your kinetic energy would be as you're speeding up. Finally, if there was a box at the bottom on the floor and you crushed that box, then you would do some work on that box and your kinetic energy would be used to do that work. But all along, no energy is lost. It's only changes forms. Here's another example. Put your palms together and rub them very quickly. What do you notice? What you should notice is that the heat that you feel is thermal energy. Okay, that energy has been as a result of the kinetic energy of moving your palms together being transformed into thermal energy. In fact, the energy that you got to move those palms together came from the food you eat, and it was stored as chemical energy, which your body then digests and uses to let your body function. Okay? Here's another example. Think of a pendulum. What a pendulum is, it's basically a rope or a string with a weight hanging at the end of it. This yellow object here is called the bob, and it's the weight. If I were to do some work on this weight by lifting it up to this height, okay, that would be work. Now the bob would have potential energy. EP is potential energy. Right now it would be at a maximum. There would be no kinetic energy, EK, as the bob is not moving. However, if I were to let it go, it would start swinging, okay? And what would happen is this energy, okay, this potential energy, as the bob swings, changes to kinetic. When it gets to the bottom of the swing, it has no potential energy, okay, zero, because there is no height anymore, but it's all kinetic energy, okay? And then as it starts going back up, gravity slows it down, speed slows down, kinetic energy goes down, but it's raising its height, so potential energy goes up till it gets up to the same height where the potential energy would be a maximum and kinetic energy would be zero. This all assumes that there is no air resistance or friction slowing this pendulum down. Okay? Our next section, 9.8, Simple Machines and Mechanical Advantage. What do I want you to understand about this section? Well, first of all, you should be able to explain how machines make work easier, not less. Very important concept. You should also be able to describe and give examples of the 6 types of simple machines, okay? You should be able to explain what actual mechanical advantage is and what ideal mechanical advantage is and the difference between those. You should also be able to solve problems for mechanical advantage or actually both types of mechanical advantage, actual and ideal, while sketching the individual forces that you would find on the different machines. A machine is a device that makes work easier, not less. They do this by either multiplying our force and or changing the direction of our force. What do machines do? Again, they make work easier, not less. For example, in our Who's the Most Powerful Student activity, if we did not have the stairs, remember we talked about this, imagine how hard it would be to get to the second floor. We talked about throwing a rope over the back. Would it be harder to climb that rope? Well, yeah, you'd have to be able to lift your entire body weight, okay? The work you would be doing would be however long that rope is, the height, times your body weight. Okay? It would be much harder to do that than to simply climb the stairs. Why? Because the stairs are actually a type of simple machine called an inclined plane or a ramp. Okay? You would not need as much force to go up the stairs to reach that height. Because why? Because you are letting the machine make your work easier but not less. Okay? You would just have to exert that lower force for a longer difference because the length of the ramp would actually be a longer distance than the height that you're raising yourself. So going up the stairs, if you didn't have friction, you didn't have to worry about friction, you would be doing the same amount of work as climbing the rope, okay? But the force would be easier, but the distance you exerted that force would be less. Follow? There are two basic groups of machines. Okay, simple machines. They have few moving parts. Okay, the first one would be a pulley. An example of a pulley might be the pulley on the rope on our flag outside the school that allows us to raise and lower the flag. A wheel and axle. An example of that might be your bicycle wheel. Okay, or a doorknob. A wedge. Example would be maybe the blade on a knife is cut like a wedge to make cutting things easier. A lever, a seesaw, or a teeter-totter would be a lever. Inclined plane, we already mentioned, would be the stairs. A screw could just be a screw, which actually holds two pieces of wood together. Compound machines. They're made up of two or more simple machines. A good example would be a bicycle. A bicycle has pulleys, has wedges, has wheel and axles, all formed together to make up the machine that we know as a bicycle. Mechanical advantage. This tells us how much that machine multiplies our force or increases our distance. Okay, there are two different formulas for mechanical advantage. One takes an output force divided by the input force, or we can take the input distance divided by the output distance. Notice the tops of these fractions, for force is output on top, for distance it's input on top. Okay, we're going to talk about what we mean by output and input in just a second. Okay. Mechanical advantage tells us how good a machine is. This means how many times it multiplies our force. You can calculate what is known as the actual mechanical advantage of a machine by the following formula. Force out, that's the same thing as output force, divided by force input. Force output is what the machine does, okay? So if a machine had to lift a box that weighed 1,000 newtons, let's say you're using a pulley system, the output force would be 1,000 newtons. Force in, or input force, is what you actually have to exert, okay? It's what you're putting into the machine. If on the pulley system I only had to use 500 newtons of force, that would be my input force. Again, the output force would be 1,000, okay? Sometimes they call the output force or the force out the load or resistance, and the input force is called the effort. Okay? So how do you calculate mechanical advantage in this case? Well, here's an example. Okay? Here we have an inclined plane. Notice it's just like the stairs, except you don't see the individual stairs. I could easily have put a piece of plywood over the stairs and it would look like this. Okay, the rope we talked about before would be going over the back right here. Okay, let's say I'm trying to push a huge weight up the stairs. Okay, the force that I put into this, we'll call it the input force or the effort, is 2 newtons. This ball weighs 10 newtons. It's called the output force or the load. My actual mechanical advantage, I take the force out, what I'm trying to lift, divided by the force I exert. So 10 newtons divided by 2 newtons is 5. That means that this machine, the way it is, multiplies my force by a factor of 5. That's big. Okay, that allows me to lift 5 times the weight that I'm actually able to lift. Okay, what's the cost of using this machine? Well, you know what? I have to exert that force this whole distance, this whole diagonal. Now, if I was just strong enough to lift this thing straight up, I wouldn't have to lift it as far, but I'd have to actually exert 10 newtons of force to lift it straight up against gravity. You follow? Ideal mechanical advantage, abbreviated as IMA. Ideal mechanical advantage means with no friction and no air resistance. It's found by taking the input distance over the output distance. Again, input distance, what you put into it, how far you have to push something, over what you actually lift the object. It does not take into account the friction as you use the machine, and as a result, it will always be higher than the actual mechanical advantage. In fact, you can calculate the the ideal mechanical advantage without even using the machine. I'm going to show you an example right on the next slide. Okay, here's an inclined plane again. Okay, notice the height of this plane is 2 meters. I want to get this ball up to 2 meters. The length of this plane is 4 meters. If I take my formula for ideal mechanical advantage, input distance divided by output distance, I see that the mechanical advantage of this ramp or inclined plane is 2. Notice, I don't even need to push the ball. I can look at it. So what it tells me that if this ball weighs 100 newtons, I have two choices. I could either stand here and exert 100 newtons of force and lift it up this distance, or I could put it on this ramp, okay, push it 4 meters, but only exert how much? 50 newtons, because it multiplies my force 2 times. That's the mechanical advantage. You follow? Okay, what I would like you to do is the worksheet on problems on mechanical advantage. Thank you.